So now we come to the concept of continuous functions. Continuous functions play a very important role in topology, and perhaps one can also argue that they are the most important concept in topology. So let's give a definition.
Suppose that you have two topological spaces X with a topology tau X and Y with a topology tau Y. Then a function f from X to Y is called continuous if, so of course this is continuity with respect to these topologies, okay? So with respect to the topologies tau X and tau Y, and this is part of the definition and we will not use it every time, we'll just call it continuous. So it is called continuous if
V is an open set. This implies that f inverse V, the pre-image of V, is open in X. So continuous functions are functions whose pre-images of open sets are open.
we can also give equivalent definitions in terms of basis and subbasis for the topology tau Y. So equivalently first is that if by is a basis for tau Y, then f inverse of B belongs to tau X for all B in By. So every basis element, the pre-image of every basis element under F is an open set, and this is because if V is an open set, then this implies that V is an arbitrary union of basis sets B alpha in By, and so this means that F inverse V is the union of open sets F inverse B alpha, and this is open by hypothesis. So in terms of basis, it is enough to check that the pre-image of every basis set under F is open. Similarly, if Sy is a subbasis for the topology tau Y, then F is continuous if and only if F inverse of any subbasis element S is open in X for all S in Sy. And this is because since every basis element for tau Y has the form S1 intersection S2, so it's a finite intersection of elements in the subbasis, and this means that F inverse of B, so let me call it B here, F inverse of B is just the intersection of these pre-images of the subbasis sets, and therefore this is open in X. So in terms of subbasis also we can just check if the pre-image of each subbasis element is open in X, and that is enough to conclude that F is continuous.
Now let me point out that the continuity of a function depends heavily on the topology, and even simple functions that look like they should become continuous become discontinuous if you change the topology. So for this we will give a non-example
of a continuous function, and you will see what I mean by this. So if F is a function from R to the a set of real numbers with a lower limit topology. So here R has the standard topology and the domain has the lower limit topology, and this function is simply fx equals x. So usually this function looks like this, and it is continuous if the range of if the topology on the range is the standard topology. However, if you put it the lower limit topology, then it is not continuous. F is not continuous. Why is it not continuous? Well, if you take a basic set of the form AB in the lower limit topology on R, then F inverse, the pre-image of this set, is the same set AB, and this is not open. This is not open in R with the standard topology, right? So this is not continuous. However, if you switch the domain and range, then it becomes continuous. However, if you consider f from R with the lower limit topology to R, again fx equals x, this is a continuous function. Continuous function, again, because if you take a basis element in the standard topology, say an open interval AB, then this is the same,
and this is open in the lower limit topology. As we have seen, the lower limit topology is finer than the standard topology on R. Now, before we move on to further examples,
we will see some equivalent characterizations of continuous functions, and this is given by the following theorem. So this theorem states that if you have two topological spaces x and y, and you have a function f from x to y, then the following statements are equivalent. So the first one is simply that f is continuous. The second one says that for every subset A, the set f of a closure is a subset of fa whole closure. So
A closure is in X and fa closure is in Y. Now for the third one, we have for each point X in X and each neighborhood V of fx, there exists a neighborhood U of fx such that f of u is a subset of V. And for this third one, we have a special terminology, and we say that if 3 holds for a point X in X, then we say that f is continuous at this point X. Now let us see a proof of this theorem. So we will show that first of all that 1 is equivalent to 2 and 1 is equivalent to 3.
So let us first prove that 1 implies 2. So we have assumed that f, so let f be continuous, and let us take a subset A of X, and we have to show that f of a closure is a subset of fa closure. Now let us take a point y in fa closure. This means that there exists a point x in a closure such that f of x is equal to y. Now because x is in a closure, this means that every neighborhood of x, say u, every neighborhood u of x intersects a, and this means that now take a neighborhood v of y. This implies that f inverse of v is the neighborhood of x. This is because f is continuous. So now you can consider this f inverse v as this neighborhood u that we have considered here, and so this means that f inverse v intersects a in a non-trivial way, but this means that v intersects f of a. Okay, just taking the image of both these sets, and this means that y belongs to the closure of fa, because we have shown that every neighborhood v of y intersects f of a. So we have given this characterization of closures with respect to intersections of neighborhoods, and this is what we are using here. So we have shown that 1 implies 2. To show that 2 implies 1, take an open set V in Y, and we have to show that f inverse V is open in X. Now to show that f inverse V is open, we will show that the complement f inverse V complement is closed in X. And if you see the definition of a closed set, you can easily show that a set A is closed if and only if A is equal to the closure of A. Remember that we already have A is a subset of A closure for any set A, whether it is closed or not, for any set A, and when it is closed, it is precisely that A is equal to A closure. Now A closure was the smallest open set containing A, and since A is closed, it contains itself, so A is included in the intersection of all the closed sets that contain A, and therefore A closure is a subset of A, and with that we have A is equal to A closure. Now it suffices therefore to show that f inverse V complement closure is a subset of f inverse V complement, which is nothing but f inverse of the complement of V. So this will show that our set f inverse V complement is closed in X. Now remember also that since V is open, this means that V complement is closed, and therefore, so this is in Y, and this is equivalent to saying that V complement is equal to V complement closure. Now if we take A to be the subset f inverse of V complement, we just need to show that A closure is a subset of A. Now from the hypothesis 2, we have that f of A closure is a subset of f of A whole closure. So if we plug in a the value of a that we take here, so this means that f of f inverse v complement closure is a subset of f inverse v complement whole closure. But note that this is nothing, this is a subset of v complement, since we have f of f inverse of a set B is always a subset of B. So this is a subset of V complement closure, but as we have seen that V complement is closed, so this is nothing but V complement. And so f of f inverse V complement closure is a subset of V complement, and this implies that f inverse V complement closure is now a subset of f inverse of V complement. And this is what we wanted to show. So 2 implies 1. Now let us show 1 implies 3. So for this, let f be continuous. Let f be continuous, and let x belong to x, and v be a neighborhood of f of x. Now by the continuity, f inverse v is open, so the open set u, which is the pre-image of v, is a neighborhood of x, and then we also have f of u, which is nothing but f of f inverse v, and this is a subset of v. So the implication 1 implies 3 is easy to show. To show that 3 implies 1, so let us take an open set V in Y, and we have to show that f inverse V is open in X. So for this, let us take a point X in f inverse V. So this implies that f of x, V is a neighborhood of f of x because f of x belongs to V. From the hypothesis, this means that there exists a neighborhood ux of x such that f of ux is a subset of V. And this means also that ux is a subset of f inverse V. On the other hand, we can simply write f inverse V as a union of all these ux's, fx in f inverse V. So why is this true? Of course, so we want to show that this is true. Of course, the union of the ux f inverse V is a subset of f inverse V. This is trivial. To show the other way around, well, you have if x belongs to f inverse V, then x belongs to u of x. So the neighborhood you choose for x appears in the union, and so this implies that x belongs to the union. So let me write it x naught, just to distinguish it from
the index here. So this implies that f inverse of V is a subset of the union of all these ux's, and this proves the fact that f inverse V is equal to the union of ux, and this implies that f inverse V is open because all these ux's are open.
Now, an important class of continuous functions are that of homeomorphisms. So what is a homeomorphism? So if you take two spaces x and y, topological spaces, and take f from x to y, a function which is a bijection, so a bijective function, then f is called a homeomorphism if both f
and f inverse are continuous functions. So here f is a bijection first of all, and both f and f inverse are continuous functions. Now we can give an equivalent characterization of the definition of a homeomorphism, and so f is a homeomorphism. F is a homeomorphism is equivalent to saying, so let me just write equivalently here. So equivalently, f is a homeomorphism is the same as saying that if f of u is open in y, if and only if u, the set u, is open in x. So this is an equivalent characterization of homeomorphisms, and we can easily show that the two definitions are equivalent. So for example, if you take a u to be open in x, then now f inverse is a map from y to x now, and so the inverse image of f inverse applied to u is just f of u, and this is open in y. So this implies that f inverse is a continuous function. So similarly, we can prove the other implications, and we have this equivalent characterization of homeomorphisms. Now let us look at an example of a homeomorphism. So we take x equals y equals the real line, and on both the x and y we put the standard topology of the real line. So tau x equals tau y equals the standard topology on the real line.
It's the same. Then the function f from x to y given by fx equals x, so this is called the identity function, and we have seen that this is a continuous function when you give both x and y the standard topology. And now this is a homeomorphism, so it is easy to check that f is a bijection because it is just the identity map, so it is a bijection. And in fact f inverse from y to x is also the identity. Okay. F inverse y equals to y is an inverse for f, and because it is the identity map, again identity function, so this implies that f inverse is continuous. So this is just a map. If you look at the graph of this function, then it is just given by the straight line y equal to x. This is the x coordinate, this is the y coordinate, and this is the straight line. Homeomorphism between x and y. There are other homeomorphisms as well, which are somewhat non-trivial. So here we take from R and Y to be R itself. Both the copies of R are given the standard topology as usual. And now define f from x to y as follows. So f of x is equal to x over 1 minus x squared. So this is a bijective function, as one can verify. So check that f is a bijection. This is not very difficult to do, and in fact you can find a inverse for this function f. So I claim that, check that g from y to x given by gy, this is 2y over 1 plus 4y squared square root, okay, is an inverse for f. So this means that f of gy equals y and g of fx equals x. So this is for you to check. Both these points are left as an exercise for you. And now the only thing to check is that f and g are continuous. And you might have seen in calculus that if you have two continuous functions and and the denominator is never 0, then the division of these functions division of two functions, the denominator not being never 0, is a continuous functions. Now the only thing to check is that both f and g are continuous, and recall from calculus, okay, on real variables, that if f1 and f2 are continuous functions from R to R, and f2x is not equal to 0 for all x in R, then f1 over f2 is a continuous function. If you haven't seen this result before, then don't worry, we will cover it later on. But if you have seen it, then you can just use this fact and determine that f is continuous. F is continuous since x, so f1 x is x and f2 x is 1 minus x squared.
And note that since f2 is restricted to the interval -1, 1, we have that it is never 0. So f2x is never 0 for all x in -1, 1 open interval. And similarly, so this implies that f is continuous. So now similarly, we have that g is continuous, because we can write it as g1y, the numerator is 2y, and g2y is 1 plus 4y square root. And one can check again that g2y is actually never 0, because it has a term y square, which makes it strictly positive, and so this is never 0. So this is for all y in R.
We have to assume that the square root function is continuous.
So this implies that f and g are both continuous, and so F is a homeomorphism. So now that we have that as F is a homeomorphism, this implies that there exists a homeomorphism, in fact, from between any open interval AB of R and the whole real line. So you can just modify the proof that that's given here, and we can have any homeomorphism between any interval AB and the real line.